In this video, we talk about techniques for evaluating limits at infinity algebraically. And if you had to guess, yes, the first technique that we're going to talk about is direct substitution. Notice that that has not changed. Whenever you are evaluating a limit algebraically, always begin by trying direct substitution. So let's evaluate the following limits. Identify any horizontal asymptotes if they exist. Here we have the limit as x approaches negative infinity of 2 plus 10 divided by x squared. Well, if I plug in negative infinity for x, that gives me 2 plus 10 divided by negative infinity squared. Well, negative infinity squared, that's the same thing as negative infinity times negative infinity, and if I multiply a negative times a negative, I get a positive, and because these are both infinitely large numbers, an infinitely large number times another infinitely large number will give me an infinitely large number. This results in 10 divided by positive infinity. What does 10 divided by positive infinity equal? Well, we are taking a number and we are trying to divide it into an infinite number of pieces. And if I am dividing 10 into an infinite number of pieces, how big is each piece going to be? Essentially 0. All right, 10 divided by positive infinity is going to be 0. So what can we do with this entire term? Let's cross it out. It becomes 2 plus 0. And 2 plus 0, well, that gives us 2 for our final answer. What about the limit as x approaches positive infinity? Again, we have 2 plus 10 divided by x squared. We can do our direct substitution. We plug in infinity for x. This gives me 10 divided by an infinitely large number. Well, if I take 10 and I try to divide it by an infinitely large number, I am going to end up with 0. 2 plus 0 equals 2. So, in this case, do we have a horizontal asymptote? Well, as we learned earlier, whenever we evaluate a limit as x approaches negative infinity or positive infinity, and the result is a real number, we have a horizontal asymptote at y equals that value. So in this case, we have a horizontal asymptote at y equals 0. Make note, very important, always label your asymptotes appropriately. Horizontal asymptotes are equations of horizontal lines. They always come in the form y equals. All right, so the main takeaway from this problem is that anytime you have any real number divided by positive or negative infinity, right? It doesn't matter which one it is. Any real number divided by positive or negative infinity, that will equal 0. Now, we could also check our work graphically. Here is the graph of the function y equals 2 plus 10 over x squared. And notice, what does this graph do as it goes to the left? The y values get closer and closer to 2. As the graph goes to the right, the y values get closer and closer to 2. We have a horizontal asymptote at y equals 2. Let's try another one. Evaluate the following limits. Identify any horizontal asymptotes if they exist. So we're finding the limit as x approaches negative infinity. Let's substitute that in for x. That gives me negative infinity cubed minus 10. Well, what happens when I cube negative infinity? That's negative infinity times negative infinity times negative infinity. Well, when I cube a negative, I get out a negative, and that will result in negative infinity in this case. I still have an infinitely large in magnitude negative number. Well, if I take negative infinity and I subtract 10, I still have a really big negative number, all right? Our answer here will be negative infinity, and because negative infinity is not a real number, we also specify d and e. Here, the limit as x approaches positive infinity. We try our direct substitution again, positive infinity cubed. Well, what happens when I cube positive infinity? I still get an infinitely large positive number, positive infinity. There we go, that looks better. All right, we get positive infinity. And what happens if I take an infinitely large positive number and I subtract 10? Well, I still get an infinitely large positive number, positive infinity, d and e. So, in this case, do we have horizontal asymptotes? Well, let's think about what these limits are telling us. Again, limits at infinity tell us about the end behavior. This is saying as my x values go to the left, as the graph goes to the left, the function goes down, 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 down. The y values go down to negative infinity. The second limit here is saying as my x values go to the right, my y values are going up to positive infinity. This function is going to fall to the left and rise to the right. We do not approach a unique number L as x goes to positive or negative infinity. Therefore, we do not have a horizontal asymptote. Because the function values do not approach a unique number as x approaches positive or negative infinity, there is no horizontal asymptote. And again, we could graph this function. Here we have x cubed minus 10, and we can verify, yes, the graph does fall to the left and rises to the right. There is no horizontal asymptote. Let's take a look at one more here. Evaluate the following limits. Identify any horizontal asymptotes if they exist. So we have the limit as x approaches infinity of 3 plus 3 sine x divided by the square root of x. 3 plus 3 sine x divided by the square root of x. Well, let's do our direct sub and see what happens. 3 plus 3 times the sine of infinity divided by the square root of infinity. Well, the square root of infinity, if I take the square root of an infinitely large number, I'm still going to get an infinitely large number. But this one's a little bit tricky here. The sine of infinity. What's the sine of infinity? Well, let's consider the graph of our function y equals the sine of x. If we were to graph this function, we know our sine curve. Sine of 0, 0 goes through the origin, and we get this nice wave. And as this function goes to positive, as the x values go to positive infinity, the function continues to oscillate up and down, up and down, up and down, up and down. But it oscillates between negative 1 and 1, which means that this quantity, the sine of infinity, has to be some number that is between or equal to negative 1 or 1. Well, if I have 3 times some number between negative 1 and 1, that's going to give me some number between negative 3 and 3. And if I have a number that's between negative 3 and 3 divided by infinity, well, what's going to happen with that? As we said before, any real number divided by positive or negative infinity, that's just going to be 0. So this whole entire term is going to approach 0, meaning we have 3 plus 0, and 3 plus 0 is equal to 3. All right, so do we have a horizontal asymptote? Yes, absolutely. Anytime we evaluate a limit at positive or negative infinity and we get out a real number, that is where we have our horizontal asymptote. We have a horizontal asymptote at y equals 3. This is saying as my graph goes to the right, as the x values approach infinity, the y values are getting closer and closer and closer to 3. Let's check out the graph of this function and verify our solution. This is what the graph of 3 plus 3 sine x divided by root x would look like. Okay, and notice we have this interesting function that continues to oscillate up and down, up and down, up and down, up and down. But as it oscillates, the height of each one of these waves gets smaller and smaller and smaller. All right? So this is known as a dampened sine curve. The height of each wave gets smaller and smaller and smaller. And as this graph continues to go to the right, the y values are going to approach 3. Therefore, we have a horizontal asymptote at y equals 3. Now, this one's not as obvious, and it is a common misconception that horizontal asymptotes cannot be crossed, when in fact they can. All right, this horizontal asymptote is crossed an infinite number of times. Well, why is it still a horizontal asymptote? Well, our definition of a horizontal asymptote says if we evaluate a limit at positive or negative infinity and get out a real number, then we have a horizontal asymptote at y equals that value. And yes, the y values are getting closer and closer to 3 as x goes to infinity in this case. All right, so there are a few instances where our direct substitution is enough to evaluate limits at infinity. Coming up next, we'll talk about some other techniques for evaluating limits at infinity.